Back Physics 30. This is the new section on fields. So the first one is FI1, investigate gravitational fields and their interactions with matter. So there's only 3 parts here, but a couple of them may be a little bit longer than we're used to, therefore only 3. So we'll look at FI1.1 in this video, Newton's law of gravitation, and then the following parts, FI1.2, gravity near the Earth's surface, and then FI1.3, satellites and weightlessness. So FI1.1, Newton's law of universal gravitation. Here we'll look at writing the equation for Newton's universal law of gravitation and explain the meaning of each symbol in the equation, and then of course solve questions involving that. So besides developing the 3 laws of motion, Isaac Newton also examined the motion of planets and the moon. In particular, he wondered about the nature of the force that must act to keep the moon in its nearly circular orbit around the Earth. So I'm fascinated with the idea that the Earth is attracted to the Earth, maintaining that orbit. Newton also was thinking about the problem of gravity. Since falling objects accelerate, at little g of course, Newton had concluded that they must have a force exerted on them, a force that we call, of course, a force of gravity. Whenever an object has a force exerted on it, the force is exerted by some other object. But what is it that exerts the force of gravity? Every object on the surface of the Earth feels the force of gravity, Fg, that we've talked about earlier. And no matter where the object is, the force is directed towards the center of the Earth, as shown in this diagram. So imagine force arrows being exerted towards the center of the Earth. Newton concluded that it must be the Earth itself that exerted the force of gravity on other objects. According to legend, Newton noticed the old classic apple hitting his head. Noticed an apple drop from a tree. He said have been struck with a sudden inspiration. If gravity acts at the top of trees and even on the tops of mountains, then perhaps it acted all the way to the moon. With this idea that it is the Earth's gravity that holds the moon in its orbit, Newton developed his great theory of gravitation. But there was a controversy at the time. Many thinkers had trouble accepting the force acting at a distance and not, of course, touching. Because in order to exert a force on something, you have to physically push or pull something, right? So the idea of an invisible force was kind of hard to accept. So gravity acts without contact, said Newton. The Earth exerts a force on a falling apple and on the moon, even though there is no contact. And the 2 objects may even be very far apart. This caused the introduction of a field, okay, many years later. And of course, a field is, you can think of a field, a force field, as a region in which an object experiences a force due to gravity. Or, as we'll look in general in the next unit, a force field where it's magnetic, electric, or gravitational. It's a region in space where a force is exerted on something else. So with that, let's look at the next page here. Example, moon's centripetal acceleration, because we'll derive something that'll help us figure out the forces being exerted. The moon's nearly circular orbit around the Earth has a radius of about 384,000 kilometers. And of course, changing that into meter sticks, multiplied by 1,000. So we might as well put that in. That's how many meters it is, the radius of the moon around the Earth. And a period of t equals 27.3 days. So yes, 27.3 days is the period of the moon, the seconds for one cycle. Determine the acceleration of the moon towards the Earth, first in meters per second squared, then in terms of how many g's are we talking about. All right. So to look for acceleration, since this is really a circular motion type question, so here you have the Earth, and here you have the moon going around. So really it's the same thing as centripetal acceleration. So we can in fact use our centripetal acceleration, or I think we call it AR equals V squared over R. So in here, of course, we're talking about radial or centripetal acceleration. And the radius, so we're assuming that we are including, because you have to include the center of the Earth there too. So the radius represents not only the altitude of the moon, but from the very center of the Earth. So all of that is the complete radius that we're talking about. So we have r. V we don't have though, but hey, from centripetal acceleration we have v is equal to 2 pi r over t. We know the t in terms of days, but of course it has to be in seconds. So we're going to have to change 27.3 days into seconds. And of course we have the radius, so we should be able to figure out everything else. So we can use a little bit of manipulation here. 1 day is 24 hours. So days cancel. Then of course 1 hour is 60 minutes. And of course 1 minute is 60 seconds. So using these conversion factors here, we can change days into seconds. And that works out to be 2.3587 times 10 to the 6 seconds. So 2.4 million seconds. So we can go back, put that into here. So 2 times pi times the radius, 384 million meter sticks that we got from up here. Our period. So that's going to give us 1,022 meters per second. That's fairly quick. So back over here, now we can take that v and substitute it into here. 1,022 squared divided by the radius, 3,840,000 I mean. And with that we get 0.002724 meters per second squared. And of course in terms of G's, so that's how many meters. So you can see on the surface of the planet, the acceleration due to gravity is 9.8 meters per second squared. So you can see it's way less up where the moon is. So we can take that and figure out how many G's there is, because I know that 1 G is 9.80 meters per second squared. So figure out how many G's that is. I think it works out to be about 0.003 G's. So really small compared to the surface of the planet. Okay, so yeah, we can manipulate the centripetal acceleration or the centripetal motion formulas to work for here. Newton said about determining the magnitude of the gravitational force that the Earth exerts on the moon as compared to the gravitational force on the surface. The centripetal acceleration of the moon, as we calculated above, here we go, 0.00272 meters per second squared. In terms of acceleration of gravity, of course, that worked out to be 0.003, sorry, 3 zeros. Now, the interesting thing here, if we compare that to 9.8, it's 1/3600th of a regular G. So out there where the moon is, it's 1/3600th if we reduce that as a fraction. So that is, the acceleration of the moon toward the Earth is about 1/3600th as great as the acceleration of objects on the Earth's surface. Now the moon is 384,000 kilometers from Earth, and here's the interesting part, which is about 60 times the radius of the Earth. Okay, so looking at the Earth's radius, if we were to take a point in the middle of the Earth, measure out to here, 6,380 kilometers. And there'll be a video coming up that I'll show you how, in fact, we get that. How do we know the radius of the Earth? It seems like it's kind of impossible to figure out, but actually it was done in ancient Greece, as we'll see. So that is, the moon is 70 times further from the Earth's center than objects on the surface. And 60 times 60 is 30, so there's that 3,600 number. So we come up with that number. So Newton concluded that the gravitational force exerted by the Earth on any object decreases as the square of the distance from the Earth's center. So in other words, the force of gravity is directly related to 1 over the radius squared. So if the moon is 60 Earth radii away, so if the radius becomes 60 times greater, 1 over 60 squared is 1/3600th times as big. So the force of attraction is 1/3600th less out where the moon is than where it is on the surface of the planet. And that's relatively interesting, coming up with that idea right there. So if the moon is 60, so compared to there, that is the relationship, and that is how the force of attraction is dependent upon the radius. All right, we'll stop the video there, and then we'll come back with part 2.